Welcome everyone. I hope everyone is hearing me. If not, then please raise your hands or do some activity on Zoom. So it's a great pleasure to continue our PCS seminar series on Zoom, but also to have our first external invited speaker and visitor, our virtual visitor via Zoom, which is Joachim Brand, Professor Joachim Brand from Massey University, Auckland, New Zealand. And let me say a few words about Joachim. He has a master in physics, which he did in 95 in Heidelberg, at the University of Heidelberg. And then he decided to become a chemist because in 99 he finished his PhD with summa cum laude in chemistry at the same university. And then he started moving. He was in Heidelberg and in Kaiserslautern. Then he moved to Seattle, to the University of Washington in the States for 2 years. And then he came to Dresden, to the Max Planck Institute for Physics of Complex Systems, where he stayed for 6 years, or 4 years, sorry, for 4 years. And this is also where we met, I think, for the first time. And then in 2006, he moved out of the Northern Hemisphere and down under, or to be more precise, to New Zealand, to Massey University in Auckland, where he rose through the ranks. And since 2010, he is professor at the New Zealand Institute for Advanced Study. And he has a number of research accomplishments, and this includes more than 70 publications in a number of well-known and good journals, and has lots of citations, and has a number of professional distinctions. And I just maybe want to mention one of them. He's currently, this was new to me, he's currently the vice president of the New Zealand Institute of Physics, which is, I think, for which the Institute of Physics can be very grateful, because I know that Joachim is a fantastic person, and we were colleagues for some time, both in Dresden and then also in New Zealand. And today I'm very happy to have you with us, and I want to welcome you again, and therefore we will make some applause for you, and everyone hopefully will hear that.
All right, thank you very much.
Wait, nothing, it didn't work. Why doesn't it work? Let's see. Okay.
Yeah, thank you.
Bravo.
Okay, good, wonderful. Yeah, thank you very much for this introduction. It's a pleasure being here and giving a seminar at your center at the Institute for Basic Sciences. I've been very excited to visit the institute, and it was a pleasure getting an invitation letter, hoping me, wishing me a good stay and many great discussions. Now, unfortunately, I can't be there physically for now, maybe later at some point, but I hope that we can still have good discussions. Yeah, so please do feel free to interrupt during my presentation as well. Okay, now I'll start sharing my screen. So we should be seeing my slides pretty soon. All right, so how is that going? Can everybody see my slides?
Yes, it's perfect.
Okay, wonderful. Okay, so I will talk about I've advertised this talk about strong quantum correlation over cold atomic gas in experiment and theory, and I would like to talk about two recent projects. Now, So this is a little bit outside my usual interests, and I thought I should just mention them before I start going into today's talk. So just in case people wonder what other things interest me, or can ask me about this later. So I've done quite a lot of work for many years on nonlinear waves in quantum gases. These are just some pretty pictures from one of our publications in this area. So typically my interest is quantum gases. So this is Bose-Einstein condensates and also fermionic superfluids, superfluid Fermi gases. Now nonlinear wave physics is of course so this is nonlinear waves is sort of classical physics, a bit of hydrodynamics, otherwise mean field theory. You don't really, usually that does not have a lot to do with quantum correlations, but then you can go into systems where quantum correlations are just very important and can't be neglected. So we did some work in one-dimensional, strongly correlated gases there as well, seeing how these concepts of solitons and nonlinear waves, pass over into these media, right? So now this already starts motivating my interest in strong quantum correlations. The other area is that when you look at superfluid Fermi gases, for example, the typical example that we have in laboratories in places around the world is the superfluid Fermi gas in the regime of unitary interactions. So this is very strong interactions, S-wave interactions between atoms. Again, this is a strongly correlated system, still has many features that you would see from mean field theories, but it is sort of interesting to see what lies beyond. Right, so this motivates my interest in strong correlations. And so now I will sort of start my talk, which is about these two projects, which are, have some relation to each other, which will hopefully become clear during the talk, but they're also a little bit separate. So the first one is on an experiment on the recombination of 3 cold rubidium-85 atoms in optical tweezers. And literally the way this works is like this cartoon picture in the background. So each atom is individually prepared, then they're put together and then they're put into one trap and see what happens. Okay, but I will talk through that in a bit. And we were involved in analyzing that. Well, we helped with analyzing, interpreting, and understanding that experiment. I'm a theorist myself, so I didn't do experiments there. And then the second project is also a recent publication or preprint about how to remove the singular short-range correlation in a quantum gas where you have short-range correlations. Right, so and how the two are related, I think hopefully will become clear during the talk. So now let's talk about collisions between particles, 2- and 3-body collisions. So if you are in free space, let's say, and you're thinking of ultra-cold atoms, and you have 2 ultra-cold atoms, then the only way they can collide is elastically, sort of, let's say in the absence of maybe strong laser fields. Even with, so now this is interesting and relevant maybe in the context, in particular in the context of ultra-cold atomic gases, because as you may know, there have been lots of experiments since 1995, or actually starting earlier. But 1995 was a date when Bose-Einstein condensation was achieved. So typically these experiments are done with atomic species like sodium, rubidium, potassium, lithium. Now, all of these, of course, are at room temperature in equilibrium. They are solids. So now in these experiments, the gases are cooled to really low temperatures, microkelvin, nanokelvin temperatures. So how does it work? Why don't they freeze? Why don't they become solid? The reason is that when they're sufficiently dilute, and they can only, the only interactions that they have is to have two-body collisions, is that even though there would be, you know, they could in principle form molecules with a state which has much lower energy, this does not happen if it's only a two-body collision. You need at least 3 particles in order to simultaneously conserve energy and momentum. So this is what is shown on the right. When 3 particles come together, you can put 2 into a deeply bound state. A lot of energy will be released, and that can be taken away by the 3rd particle, and you can conserve momentum conservation at the same time. Right? If there's just 2 particles coming together, they cannot go into this deeply bound state because they cannot get rid of the energy that would be released there. Right. So then the trick is for the ultra-cold gas experiments is to keep gases sufficiently dilute such that 3-body collisions happen only rarely. So the first idea is naive thinking is that 3-body collisions are bad. On the other hand, they're there all the time for these ultra-cold gas experiments. So typically there is something that limits the lifetime of an ultra-cold atomic gas, because eventually when 3-body collisions happen, atoms will be lost. So what happens is they just go into some deeply bound molecular state. There's a lot of energy that will be released, much more than the atom traps can hold. So they will basically fly out and be lost. Now, this process of 3-body recombination is quite important. For example, it was used to detect Feshbach resonances, where the magnetic field is changed. So this was a gas of, I guess this was catalytic experiments of probably sodium atoms. And then changing the magnetic field, there are atomic scattering resonances, molecular resonances that are magnetic field dependent and that can be tuned. So experimentalists notice that when changing the magnetic field, the scattering properties change, and in particular at a specific field strength, they see a huge growth of this, a huge increase in losses that they have. Okay, so the typical kind of graph that they have, there is number of atoms here on the top. So they just wait for a little while, prepare their gas, they ramp the magnetic field, wait for a little while, and then see how many atoms they have lost. And this is how they see that 3-body recombination has taken place. And virtually almost everything we know in terms of experimental data on these 3-body recombination comes from experiments like that. Simply observing loss in experiments, where you have a large number of atoms or a gas, you prepare them, and then you wait and you see that you lose them. There's one experiment I should mention where so this was, I think, University of Ulm. I didn't put a reference here, but where they managed to, group of Johannes Hecker-Denkschlag, where they managed to trap the molecules that were created. Yeah, so by the process here on the right. So there's some molecule created. Usually these fly out of the trap, but they ionize these molecules right away and then trap that in a ion trap, in a penning trap. So at least they could have a look at these molecules. Right, now typically one would expect, so I mean there's quite a lot of theory on how 3-body recombinations happen. I don't want to go into the details of that. here at all. I just want to mention that there's some scaling theory that at least for large scattering length, this recombination rate is expected to scale with the fourth power of the scattering length. Right, so this is the reason essentially that here at the Feshbach resonance, where the scattering length becomes really large, this three-body recombination process becomes so dominant. And the other one is that it scales with the third power of the density. So this comes just from the fact that when you have higher density, then you expect atoms to meet more often, or that you have these events where three atoms meet at the same time happen more often. Right, so now the experiment that I want to talk about was done by these people here at the University of Otago. So here on the very left, that is Mikkel Andersen. He is the PI of that experiment, his postdoc Marvin Weiland, and then Eyal Schwartz on the top. Bottom right is Luke Reynolds. He was a master's student and he's the first author of this paper that we published. And then on the top right is Ulrich Ebling, who was a postdoc in my group and helped with the theory side. Yeah, so what this experiment planned to do was, or did, was for the first time prepare these three atoms individually and put them together. And then that has some benefits, and has some benefits. And the benefit is in that you have an actual individual elementary process. In particular, you can distinguish whether you have actually a three-atom process, so whether you lose all three atoms at the same time, or whether maybe you have consecutive processes where two atoms are lost, which can still happen by optical, if optical transitions are involved. Right, so their experiment, so here, at least on the left, you already see some optical table. This involves lasers, a lot of optics elements. Then there is a vacuum chamber. Inside this vacuum chamber is a telescope, basically, some clever optics. And here you see a view through the vacuum chamber, and you see a red dot there, which is actually the cloud of cold atoms that they're holding there. I believe that is probably in the phase of a fairly early phase of the experiment, where there's still a number, maybe some thousands of atoms in a magneto-optical trap. And later, this number will be reduced to 1, 2, or 3. On the right-hand side, there's a schematic of that experiment. Yes, so the magneto-optical trap holds some atom vapor there in the first place. Then this orange beam is turned on. That's a far-off resonant trapping beam or an optical tweezer. It has a very small focus, very small volume in which atoms can be trapped just by the fact that it is a red-detuned laser from an atomic transition, which produces an AC Stark shift, which produces an attractive force essentially for the atoms. So the atoms are pulled towards the intensity maximum of this beam. Right, and there's some imaging optics as well. Right, so now the question is how to prepare a single atom, first of all, in this trap. So previously we talked about two particle collisions, that they can only be elastic. Now, if you at the same time illuminate these atoms with a laser, there's a few more tricks that you can do. So here, the lower part would be the potential energy curve of two atoms meeting as a function of the separation of the two atoms. So there's a typically attractive van der Waals potential tail and an attractive van der Waals potential. In the bottom of this potential well, there will be molecular bound states, right? But we're never getting there, right? So we're scattering in with very low energy, so that's almost zero energy here. Now, the laser beams that are turned on can induce transitions to some upper state, and there are some higher molecular states that have some asymptote where one of the atoms is excited, is an excited state, for example, that are seen here, and there are various processes that can can be addressed. And here, in particular, the experimentalists are using one process that would actually that increases the energy of the atoms while they're colliding. Right, so normally you would say that's maybe not so good because it heats up the two atoms. So that would be the process C, where both atoms are heated up and then they have to be cooled again. Yeah. So there's also lasers which are not shown here, which can cool the atoms when they're sitting in this trap. However, this process also has other outcomes. One of them is that the atoms get so much energy that they're both lost from the trap. Yeah, the trap is a finite potential well, sort of. But it's also relatively likely that, that what can happen is that kinetic energy is mostly taken by one of the atoms, whereas the other one has low kinetic energy, stays in the trap, and one atom is pushed out. And the end result is that from two atoms now you've lost one atom, and you only have one atom remaining, right? So this is a mechanism to induce single particle loss. And this mechanism will stop when there is a single atom left in the trap. That is the important thing. So for this reason, this mechanism can help you to prepare a single atom in a trap. When you start with many, and at the end of the day, you might get unlucky and that all of the atoms are removed. Otherwise, you're left with one atom. Then there are no light-assisted collisions anymore. And the process will stop. Otherwise, it will continue. And you will continue losing atoms. So again, here, yes?
Ask you for a question.
Oh, sure.
Can you go, please, to back one slide? Yes. So this transition which you mentioned basically excites an electron, I guess, inside one of the atoms, right?
Yes.
Through the laser field. Just in brief, why is that not affecting the condensation properties of your gas if the atom is not interacting with another atom? So if you have, so to say, a single atom, you basically do not heat up nothing. So this is just energy stored temporarily in the electronic shell, and then it's released probably again as a photon. Is that what happens?
Yes, yes. There's spontaneous emission, which will bring this atom back to the ground state.
But
now,
its kinetic energy, so to say, is not affected of the whole atom.
Well, it is affected a little bit. So the kinetic, the spontaneous emission down to the ground state will have a recoil. The photon that is leaving gives some momentum kick. So it is a heating mechanism. Right, so some heating is happening. Here in particular, they do it with this mechanism with the blue arrows, where they actually store some additional energy in this excited state. Well, actually in the pair of atoms. So kinetic energy will be higher, and that is exactly what is planned to be done here. So this blue transition is can only excite really if two atoms are approaching. So if it is just a single atom, it will be off resonant from the atomic transition. This is blue detuned from the just single atom transition.
Okay.
So only when the two atoms are approaching and they're on this, so then there is this repulsive energy curve of the excited state. That is the one that can be accessed.
Okay, thank you.
Right. Okay, so now we have a mechanism for loading a single atom, and this was demonstrated here in this Grünzweig paper, Nature Physics. So this is from the same group, Mikkel Andersen's group, and I was not involved at that time at all, where they first demonstrated the single atom loading mechanism to be very efficient. So the integrated signal here, I think it is actually the number of atoms, or the scale is such that it's normalized to the number of atoms. So the big peak shows that cases where they found one atom, and the little peak shows where they have 0 atoms, and then very much suppress the case where still 2 atoms are in the trap. Right, so now is our the recent experiment. So instead of just making only one of these tightly focused laser beams to create an optical tweezer trap, they make 3 of them. Right, so this is not very difficult. I think they have gadgets which are called acousto-optical modulators, where they can split the laser beam into 3 beams and separately focus them with all but the same lens. So basically these are 3 optical tweezers, and they can be manipulated and steered. So they do their process of cooling. So this is Raman sideband cooling. This is a technical term, is a way they can cool atoms when they're in these optical tweezer traps. It again uses optical transitions, and then they do the light-assisted collisions in order to remove all of the atoms except one. And then with a very high probability, they have one atom in each of these laser focuses. So these atoms, while they're in the optical tweezer trap, they can be imaged and can be detected and can be identified that there is a single atom in there. This is the verify step. And then they, with their acousto-optical modulator, they modulate these laser beams in order to merge the trap. So move them towards each other, essentially. And then in order to increase the density and increase the probability that they interact, the laser power is ramped up to make an even deeper trap, a narrower trap. Right, and on the right-hand side is some readout from that. So then you wait some time, and then you see your image again, and you can detect whether you have 0, 1, 2, or 3 atoms. Right, and you can do that with various hold times, and then you get a graph that looks like this. It shows you the loss dynamics in these triads, so 3 atoms in the trap. 3 atoms were prepared, that was checked. And then red here shows a probability of 3 atoms remaining as a function of time. Yes, so yellow, orange is 1 atom remaining, then blue is no atoms remaining, or green is 2 atoms remaining. So one thing that you can see from there is that, apparently 3 atoms will not remain for very long, but however, the hold times here is in seconds, right? So this is actually a pretty long time scale, which it takes for these 3 atoms to disappear. There's almost no rate of going down to 2 atoms, right? So that a single particle is lost, a single atom is lost from the trap. That is must be a very rare process. So then there are these 2 other processes. One goes where 2 atoms are lost from the trap, 1 is remaining. So this could go with a light-assisted 2-atom collision. And these were also measured here. Or when you go to the blue curve and you lose all 3 atoms at the same time. Right. So these are the different processes, and you can basically parameterize this process, these processes with the rate equations that are written on the right-hand side. Right, so these rate equations give, R3 stands for 3 atoms remaining, R2 for 2 atoms remaining, and so on. These are fitted then to the curves, to the experimental data, and then you can extract these coefficients, gamma 1, gamma 2, gamma 3.
Joachim, sorry to interrupt you, but we have a question from Ivan.
Sure, please go ahead.
Yes, Ivan.
I hope we will not be down because my question as usual. Now I'm connected to the wired net. As you mentioned, there are many different experiments and frameworks to describe this trapping of atoms, manipulating them together. Can you please specify what is new in your setup, which is pretty fresh, so this year basically? So what are these new ingredients which were added from theory and from experiment? Thus it's PRL and quite interesting, because I missed this sort of.
Right, so what is
where the frog jumps in the lake?
Yes, sure. So the question was, what is new compared to other things that were happening in ultra-cold atoms? So the new thing is that just 3 atoms were prepared, and then their collision studied. Right. So previous studies of 3-body recombination had usually worked with large gas clouds with thousands or sometimes millions of atoms. Now, if you have many atoms, you can, of course, you notice loss by just seeing that the particle number drops. So this was done in these early experiments also from Kettler 1998 that I showed, for example, detecting Feshbach resonances. However, you don't know whether your loss process is a single atom loss process or a 2-atom loss process or a 3-atom loss process, or maybe even higher atom number loss processes. It's very difficult to distinguish these processes if you can only see that the number of atoms is decreasing. Right?
So the main thing is that there are just few atoms here.
In this case, there are exactly 3 atoms. So that is the difference.
Okay. And how is it checked that it's exactly 3? As far as I understand, experimentalists manipulate them by some lasers and laser traps, basically, right? But how can they be sure that it's only 3 and not more?
Oh, yeah, exactly by this process here. So the laser focuses are separated in space. They're imaged through the, maybe let's go back here. So there are now 3 focal points of this optical tweezer, and imaging goes through the same lens, right? So they know they have 3 focal points, and then they take images, and the images are like the one that you see here on Verify. Okay, now this is done, I'm not exactly sure how long you have to illuminate, but this is, the atoms are held in fairly deep chap, and then they're illuminated with light, and fluorescence is measured. And so this is not a single photon process, it's actually many photons. You integrate over some time, and then you see how much scattering rate there is. And from the scattering rate, you can then know how many atoms are in there, which is what was on this slide here. So 1 and 2, you see the pictures look brighter for 2 or for 1. So this is the integrated signal that they have. There is a discrete, a difference in the signal that they're integrating here from the fluorescent signal, which tells them whether they have 1 or 2 atoms. Right, so So this is really grabbing 3 atoms at a time. You can verify that before you do the experiment. After the verification step, there may be some further cooling, but basically that is it. You know that you have 3 atoms. And then you do the merging, and then again you measure how many atoms you have. Right. So in that sense, it is really quite different from what has been done before, because now the single atom, 2 atom, and 3 atom loss processes can be distinguished.
Okay, thank you.
Does it answer your question?
More or less, it's much more clear at least.
Okay, now I get connection that my internet is unstable. Can you guys still hear me?
We do.
Yeah, okay. Right, okay, good, great. So, so let's move on then. So actually next, yes? Was there a question, sorry? No.
No.
Good, okay, well, maybe I'll have to put it back there to the top. Okay, so I just want to talk a little bit about these rate equations and where they come from. Right, so we've derived these rate equations you can derive them. It's a fairly simple process, actually starting from a Born-Markov master equation. Right, I just want to talk through this because there are some assumptions in here, and that is sort of important. So the assumption is that loss happens at very short range. It happens quickly, and that there is no memory in it. Right, and then the Born-Markov equation is master equation here is a master equation time evolution of the density operator. First term is just the conservative dynamics in the trap. And then here this is a sum over 3 different loss processes where you have a single particle loss, 2 particle loss, and 3 particle loss. Right, now this formally then you can write this density operator as a sum of 4 different terms which strictly have 0 particles, 1 particle, 2, and 3 particles. Right, and then basically from there it's just a bit of algebra to go to get to these rate equations. And now you have some interpretation of what the gamma rates are, which are the fitted parameters that are fitted in the experiment. So gamma 1 is just the one-body loss rate. Okay, but you may remember that was very low in the experiment under the conditions where it was done. So there are 2 different two-body loss rates depending on whether 2 or 3 particles were left in the trap, and then gamma 3 is a 3-body loss rate. So the 3-body loss rate has the kappa 3 term in there, which was a coefficient that appeared in the Born-Markov equation. So that will come from atomic physics, right? That's the probability when 3 atoms come close to each other that they actually recombine and form a molecule. So that will maybe depend on magnetic field and things like that. But the other term is interesting here as well, which is a 3-particle correlation function. So it gives us some information about correlations in this quantum mechanical 3-body problem.
Joachim, sorry, I have a quick question.
Sure.
On the last slide, can you please explain how you get these strange prefactors of 2, 2 by 3, 2, I mean, because they of course affect your rates then.
Yes.
So where do these, because do they come from the master equation or somehow your atomic physics is important for these prefactors?
No, they just come from the master equation and from knowing that we have 3 atoms in the quantum state as we start out with it. So this is really, it's just, and actually the numbers would be different if we had a large atom sample, but they're just, sorry, what is the word? So it is really just counting of different possibilities.
I see.
Yeah, basically
So
putting.
it's just a combinatorial factor. So.
Yeah, it's exactly, they're combinatorial factors.
Okay, perfect. Thank you so much.
Right, and there's actually no approximation involved in getting them. I guess an approximation would be that these these densities or correlation functions are time independent, which is an approximation here. That they are not not themselves dynamic quantities, but otherwise this is sort of really straightforward algebra. Okay. Right, so then what is typically done, also in particular in previous experiments where you had large atom samples, large gas clouds, is that you integrate and you replace this 3-particle correlation factor here by the 3rd power of a density. Again, there's a combinatorial factor, and this combinatorial factor depends a little bit on what type of gas you assume. But the one that is shown here is specific for the fact that it's 3 atoms. So this gives us the 8/3 factor here. And the atom density, in this case, we know from the fact that we have 3 atoms, we know the geometry of the trap, and we also know the temperature, which is measured separately. Okay, I didn't talk about that, but the experimentalists have a way of measuring how much energy basically their 3 atom sample has. Right, so if you put that in, and then you take a value of kappa 3 that is known from the literature. So it is known from, I mean, the paper that I'm citing here is actually a theory paper. This was done with some model calculations, but it basically agrees, this theory paper agrees with experiments that were done at Gila, and I think there were experiments at MIT as well, that for specifically rubidium-85 atoms measure these 3 atom recombination rates. Now, there is a little bit of uncertainty in there, or let's say, one thing that is a little bit dodgy, as I mentioned before, in these experiments with large atom samples, they also usually have significant 2-body loss rates, because they always have lasers on, and there could be 2-body loss processes that are laser induced. And it's not so easy to completely get rid of them and model them out in the analysis. Right, so maybe there is some uncertainty to this. And also I think there was some scaling involved in terms of the scattering length, because not all experiments were done at the same magnetic field setting and the same scattering length. So there should be some uncertainty in this value, but it will not be huge uncertainty. But now if you put in these numbers, you see you get the blue dashed line that is here in this graph. And the experimental data is down there in the dots with some error bars. And you see that it's a logarithmic scale. So it's basically a 3 order of magnitude difference, which is quite a lot, right? So that is not so easy to explain from maybe this, kappa 3 value not being very accurate. Right, so there's, in that sense, we have, so gamma is, of course, is the inverse lifetime. So what we're seeing here is the lifetime being longer by 3 orders of magnitude than what you would expect, basically naively from extrapolating known facts about the 3-body loss rate in rubidium-85. Rubidium 80.
Joachim, I just interrupt. This calculation of these uncorrelated thermal atoms, gamma-3 loss rate, is that depending also somehow on the temperature, or is that or on the kinetic energy of the gas?
Okay, so there is some temperature dependence here in the density. Because the higher the temperature, we have a Gaussian trap, the higher the temperature, you know, the more spread out this gas cloud will be, the lower the density. The kappa 3 is assumed to be just an atomic physics constant.
Okay.
However, this is a constant that is essentially calculated for 0 temperature. Now, I don't think there is a huge dependence here, although it could be a factor, right? Because we will now have to look for possibilities that explain why there is this big discrepancy.
Okay.
Right? So there are a number of questions of whether the theory that leads to this kappa 3 values is still valid, of course, right? So one thing could be that we are at some finite temperature. It's not exactly 0 temperature. The other thing is that, you know, there's lasers, there's a strong trap. And it's not clear whether that theory should still work.
Thank you.
So this is basically actually what we have on this slide, the question of how to explain now this reduced three-body loss rates. You know, so the tight optical trap could modify kappa. Yeah, finite temperature, I didn't put it in here, could do that as well. There could be the fact that the light field is actually is quite strong. So we're in the focus of this is a schematic taken here from a different paper from Cindy Riegel's group, who also do these optical single atoms and optical tweezer experiments. Yeah, so the laser light is very intense. Right, and I don't really want to talk about these possibilities, also because it's something that I don't really know that much about. And we were thinking in some other direction, which is that you know, we have interacting particles in there, and the assumption that they are completely uncorrelated, even though they're interacting, is maybe not such a good assumption, right? So even though we have a decaying quantum state, we still have a quantum state where there's also conservative interactions. Right, so then how could that influence the result? Now, rubidium 85 at very low magnetic fields at which they're operating there has negative scattering length, which means the mean field interactions are actually attractive. So again, naively, you would mean, oh, that should lead atoms to clump together. When they clump together, their density increases, and their three-body recombination rate should go through the roof. And yes, that would actually be bad. Okay, but now let's think a little bit further. So first of all, I would like to simplify the situation a little bit by projecting it down to one dimension. So this is motivated by the fact that the trapping potential here is quite asymmetric. So there's one weak trapping axis called omega x here, and then there's two tight axes, the transverse axis, which have a much higher trapping frequency. Now, as a caveat, the temperature is so high that we're not just in the ground state of the transverse trap, but at least we could, you know, pretend for a moment that that was the case and see where that leads us. Right. So then you're back to one-dimensional quantum gases, and one-dimensional quantum gas with contact interactions, which is in this case attractive, has states as they're showing here on this graph. Okay, so this is the energy of of actually two atom states in, I think, a box with periodic boundary conditions with contact interactions. Here on the x-axis is -1 over gamma, but it's basically -1 over the scattering length, interaction strength, if you want. So we're a little bit right of zero here, where interactions are attractive in principle. So we have a bound state that has a very low energy. So the bound state or ground state, as it's here on the left, has a wave function that looks roughly like this. So it will exponentially decay and form a cusp. So again, so this is just two particles. So two particles will have a high probability of being very close to each other, and then a third atom comes, that would not be good. On the other hand, then if you look at the excited states, they still have to have the same cusp, but now they have nodes, and these nodes are very close to the cusp, in particular, as you go to very strongly negative scattering length. So they basically avoid each other. And one prominent example of a gas many-body system with these properties is the super-Tonks-Girardeau gas, which is indicated here. So this corresponds to an excited state where exactly these bound states, or quantum solitons, if you want to call them, do not form. And instead, the atoms are anti-correlated. So there's this particular limit where 1 over gamma is 0, which is a Tonks gas where, if you're not in the bound state, then you're guaranteed basically for atoms not to be at the same place. They're completely anti-correlated, similar to, this is also known as a phenomenon known as fermionization, similar to what would happen with spin polarized fermions, who avoid each other due to the Pauli exclusion principle. Right, so our explanation, and the explanation here is really more like a speculation, I have to admit, is not a thorough theoretical investigation, is that because we are not at very low temperatures, so we rather have excited states than ground states. So projection onto ground states would be quite low. So we mostly have excited states, and they are anti-correlated, and then would lead to a reduced free-body recombination rate, right? Because when two atoms already do not meet each other, then free-body recombination will also be suppressed. Okay, so just seeing whether the effect assumes that in integrating over the density and the atomic physics constant kappa 3, we put in the local pair correlation of, well, three-particle correlation factor for a super-Tonks-like gas, which is highly suppressed with its interaction constant gamma to the 6, and gamma is here the Liebniger constant, but it's proportional to the three-dimensional scattering length A. Right, so this gives a very strong suppression, 6 orders of magnitude from the original expectation that we have uncorrelated thermal atoms, but it's also sort of the worst case scenario and is not completely, there are many assumptions that are not completely true, that we have a 1D gas. We have also put in something which is incorrect, is that or inconsistent in some sense, that we said, it is a super-Tonks-Girardeau gas, so it's very one-dimensional and anti-correlated, but we took a density that was assuming that that we actually have a three-dimensional gas, which was not correct. And if you if you try to put in some other values, assume that you have consistently a one-dimensional gas, and you would really be cold enough to cool into one-dimensional gas, you would actually get to that red line up here. But so this is just motivating basically that interactions can lead to correlations, anti-correlations in this case, who could lead to the suppression effect. Okay, so this is the first part of my talk that I'm concluding, and I'm happy to take any questions here. And when I look at the time, I see that basically that hour is over. So maybe I'm wondering I should probably, in fact, more or less stop here and take questions, and then later have discussion as well.
Well, we start a bit later, so I think if you want to add, let's see whether there are some questions right now. And if you can manage to give a short wrap up for another 5 to 10 minutes for the second part, that would be fine, I think. But you can as well also skip it. That's up to you.
Right.
Let's maybe first, let's give you some time to think about these options and see into the audience whether there are any questions on what we heard so far. Maybe I should just start with one warm-up. At the very beginning, well, somewhere at the beginning, you showed the experimental results of these evaporations of these 3 atoms, and there was a very low probability to remain with 2 atoms in thank you, 2 atoms remaining in the trap. Is there some intuitive reason why that happens, which you can offer?
Yes, well, under the conditions of that experiment, okay, first of all, I talked here about a mechanism that could lead to 1 atom loss, right? So 1 atom loss is actually not so easy to get. So, so how can you lose a single atom? One possibility is that the vacuum is not very good, and you have some background hot atoms floating around there with 300 Kelvin. And if one of those hits, you know, the atoms in your optical tweezer, that will be enough kinetic energy to knock out a single atom, right? Another mechanism would be this one here, but this requires a specific bluely tuned laser for these light-assisted collisions, where again, you have a 2-body collision, but you've added enough energy that one atom has enough energy to escape the trap and the other one doesn't. If you have a conservative collision very deep down in the trap, where you keep the energy, it is very unlikely to lead to a single atom loss, because they're already cooled to such low temperatures that basically evaporative cooling would not happen anymore, right? So, so what is left is 2-body loss processes and 3-body loss processes, right? So 3-body loss is the 3-body recombination we talked about a lot, and 2-body loss processes can also happen in the presence of a laser field and in the presence, and in fact, it was also measured in this experiment. I didn't show data here. It is actually quite significant rate, but it was also tested that this very strongly depends on the intensity of the laser beam. So when the intensity of the laser beam is changed, this 2-body loss rate changes quite a lot, whereas a 3-body loss rate doesn't.
Okay, other questions, audience? I don't see any raising hands so far.
Okay, if there are no more questions right now, I'd be happy to try to give you a 5-minute wrap up of the main idea of the second part of my talk. I think this is also very cool. I like this this topic a lot, and I think the idea, it shouldn't take too long to explain the idea. So the problem here is that, okay, so let's say if you do scattering with ultra cold atoms, again, here's a 2-atom scattering potential, or potential energy of 2 atoms approaching each other on the left, there's this deep well, we already saw that. So then when you look at the wave function of a scattering atom, you see something like what is plotted here on the right. So there will be many nodes of this wave function, a lot of detailed structure as inside basically this well. However, if we have ultra-cold atoms, they will come at very low scattering energy, very low scattering momentum. So the structure of the wave function far away from that doesn't see any of that. So there's only the scattering length, which is this parameter A here, which is really important to determine the properties of the gas, the many-body physics. Right, now for that reason, one, for any type of calculation, typically we ignore the short-range part of the correlations and replace it by the scattering length. Now, in order to do a calculation that just looks at the scattering length, basically we use then a model of contact interactions. Now, in contact interactions, you would extend the wave function beyond the scattering length to very short length scales and just assume that they solve the free particle Schrödinger equation. However, that leads to wave functions that have a quite singular behavior at the origin. Right, so this is encapsulated in the beta-Piles boundary condition. The idea goes back to beta and Piles, where in the 1930s or so they tried to solve an idealized problem of the two-body problem of bound state of the deuteron. Right, now it depends on how many spatial dimensions you have. In one dimension, you have a wave function that has a cusp, yeah, so that has a that is still continuous, but it has a discontinuous first derivative in 1D. Now in 2D, you already have logarithmic singularity, and in 3 dimensions, you actually have a hyperbolic singularity in the wave function. Okay, so all of this is well known, but now what we want to do is we want to basically to do an expansion in a plane wave basis. Let's say do an exact diagonalization calculation where you start with smooth basis functions and then try to approximate that. Okay, so let's go to this side right away. Now then here in black you have the cusp, and let's say you want to approximate that cusp with the superposition of plane waves. All of you know that that doesn't work very well. So you will need many plane waves because it's now a non-smooth part of the wave function that will converge very slowly. In terms of quantifying that, so this convergence of the energy to the exact ground state energy, this was done here, for example, as a result from 2015 from some quantum chemists who wanted to do that in a harmonic chap using harmonic oscillator basis functions. See, this goes very slowly, 1 over the square root of the number of basis functions. A little bit better for plane waves. And then a thing that people typically do, also, let's say, methods from field theory, lattice QCD, that kind of approach would renormalize coupling constant. So would still use contact interactions, but with a renormalized coupling constant. So you can get a better convergence there. But what we're doing is something different. It's a so-called transcorrelated approach, and I will explain that in a minute. Should go pretty quickly. So for this one-dimensional problem, it can accelerate the convergence by a full order here. So 1 over m to the 3, where m is a number of basis functions of plane wave states that you put into an exact diagonalization problem, essentially. Right, so what is the idea? So this transcorrelated approach is the following. The full wave function with its singularity or cusp properties is written as the product of e to the tau times some other smoother wave function phi. Okay, e to the tau is a Jastrow factor. It's a factor that is written as a sum of pair wave functions, and the idea of this is to encapsulate the short-range correlations. Now phi is a smooth or smoother function. It carries long-range correlations, and then the idea is that we want to use exact diagonalization to basically encapsulate these long-range correlations. Right, so when you start with a time-independent Schrödinger equation as is written here, and then substitute with this e to the tau factor, you can multiply another e to the minus tau from the left, and then you get the lower equation, which is, has the same energy eigenvalues, and it is a similarity transformation, corresponds to a similarity transformation of the Hamiltonian, of the quantum Hamiltonian. So that one, okay, and the idea goes back to Boyce and Handy, and recently it was revived in the context of exact diagonalization in quantum Monte Carlo by Duro and Alavi. So this transcorrelated Hamiltonian has new terms, and these new terms come from derivatives of this Jastrow factor. And they're a little bit tricky because it's non-Hermitian, even though the eigenvalues are still real. So this is the second term, is a non-Hermitian term. And there are 3 body interactions. But thankfully, there are no higher than 3 body interactions in it. However, it is less singular. So this is why then it can also accelerate the convergence of these basis set expansions. Right, I guess that is the basic idea. We did this in 1D and in 3 dimensions. The wave function actually does become smoother. We were able to prove that in 1 dimension, and in 3 dimensions, we basically have, we don't have a mathematical proof, but we have sort of evidence and, some numerical evidence, let's say, and some reasonability arguments. And then we see so this is now the example in 3 dimensions where we see that with this transcorrelated approach, indeed the ground state energy is also for a fairly small number of basis functions is very well approximated. And then we did some benchmark. Okay, so we're using a quantum Monte Carlo technique then to go beyond 2 atoms, because this becomes now a large number of, Hilbert space becomes very large. And then we compare to other benchmark calculations, and essentially the message here is, I don't really want to walk through this, this is 3 particles. Our data is the purple dots for 3 particles, and for 4 particles, I'll just show you a graph with some error bars. Our data is a new one here for, this is 4 fermions at unitary interactions. We can reduce error bars compared to previous quantum Monte Carlo calculations by, at least 2 orders of magnitude. So it works. Okay, now, not sure how long that was. It may have been a bit longer than 5 minutes, but basically that is it. That's what I wanted to say here. And there are references here, and some other of my collaborators, especially on this project, are here circled. So this is Ali Alavi in Stuttgart. The picture was taken while we were on sabbatical in 2017. Peter and Ulrich are from my group, and there's Honjung, he's a local collaborator in Stuttgart. Okay, that's all I wanted to say, and I'm happy to answer any more questions if there are any. Thank you.
Doesn't work, I don't know why. Okay, thank you very much, Joachim. And I think we can still take a few questions before we'll have a break. So, yeah, please, questions. There's a question by Ivan. How do I do this?
Yep,
Oh,
I did it.
you already unmuted him.
Mm-hmm.
Yeah, go ahead, Ivan.
So I wanted to ask, are you also working with the condensates of cold atoms when you have some macroscopic number of particles?
Well, yes, I mean, I do, but I'm a theorist, so I don't have experiments. So the experimentalist or the experimental project I showed earlier, that was Mikkel Andersen's group, and they do currently the single atom trap experiments. I know that Mikkel has previously worked on, so I think he was a postdoc in the Phillips's group where they did Bose-Einstein condensate experiments. Yes, we have some other projects also where we work with sort of fermions recently quite a lot, where we do fermionic mean field theory, Borough-Liebov-Duchenne equations. And then, and then this recent quantum Monte Carlo work, I think we also would like to get back to having larger number of atoms than just 3 or 4. But sort of these were these benchmark calculations where we could reach very high accuracy.
As far as I understand, in the system of cold atoms, they can behave as fermions or bosons depending on some parameters, maybe depending on the atoms themselves.
Well, the atoms themselves are fermions on bosons depending on, on the constituent elementary particles, which means that if you change isotopes, you can go from fermionic to bosonic elements. So that an example is potassium, for example. There are bosonic isotopes and fermionic isotopes. So in principle, you could even have in a single experiment, you could change that. Or of course, there are experiments where they already from the beginning load 2 different types of atoms, some fermionic, some bosonic. Now, there is, of course, then other reasons, let's say, which is more condensed matter correlation physics, where you can have effective fermionization of bosons. So this was this Tonks-Girardeau gas, where you start out with a Bose gas in 1 dimension, make interactions, contact interactions very strong, and then they behave very much similar to a fermionic gas. But in 1 dimension, sort of there's this duality between bosons and fermions. You can basically always replace interactions, at least short-range interactions, with sort of the quantum statistics.
Okay, I understand that maybe it's a little bit off topic, but I'm curious in hybrid systems where you have fermions and bosons. So do you think it's possible to make a hybrid system in a system of cold atoms when you have some fermionic and bosonic subsystems somehow interacting with each other?
Yeah, so there are experiments that have both fermions and fermionic atoms, and I mean there are quite a few examples of that. You can have a mixture of bosonic and fermionic atoms, both in the same trap. There are experiments with that. Actually, there's one experiment in New Zealand here in the group of Niels Kjærgaard, also University of Otago, who has, in principle, both. I don't know whether he has published any papers where he put both together. But yes, this is done. The other example that I'm thinking of right now is, of course, the fermionic superfluids that I'm quite interested in. So people typically start with a fermionic gas of atoms, but then they ramp into a regime where they dimerize. So you can have a Bose-Einstein condensate of dimers, and these are now weakly bound dimers of fermionic atoms, which are of course bosons, right? And then if you, for example, imbalance the number of fermions, which you can also do, that you have more spin up than spin down fermions, then only the spin down fermions, each one of them can pair and form dimers, but you still have fermions left over. So experiments with these are being done, you know, have been done, and there's actually quite a bit of interest in understanding these systems. So, for example, in these systems, you can, you know, you expect to see FFLO states, these full differential Larkin of Chinikov states of modulated superfluid order parameter, which is, you know, has been an interesting topic for a number of years, and still it has not been very clearly seen, at least not in three-dimensional systems, for example.
So it's three-dimensional. Is it possible to make quasi two-dimensional systems? And
Yes,
is it possible to separate somehow in distance fermionic and bosonic atoms?
You're thinking of a layer of fermions and a layer of bosons. Yeah, it could also
It would be just, maybe it's not necessary, but it's just easier for my imagination to think of it like this. So
yeah, I'm not aware of an experiment that has done exactly that. Quasi two-dimensional experiments, there are quite a lot now, actually. So they're probing, for example, BKT, Berezinski-Kosterlitz-Thouless type of transition physics in two-dimensional gases, other strongly correlated physics. I'm not sure whether there's any one that has specifically looked at both Fermi mixtures, but yes, you can also have, you know, have bosons on one layer and fermions in another layer. I think that may be a little bit more difficult to achieve experimentally. But in principle, it is possible to have different trapping potentials for different species of atoms. It is a little bit tricky, I think, but it has been shown and demonstrated at least that it is possible. So you could trap a fermionic species of atoms in one layer and then a bosonic species of atoms in another layer.
Okay, thank you.
Okay, more questions? Let me ask maybe a very short and simple one. At the very beginning, you discussed Feshbach resonances and evaporation of atoms through three-body recombination processes.
Mm-hmm. Yeah.
Now, in that process, which you explained very nicely, are really all three atoms? So basically, three atoms meet, and as far as I understood, two can form a pair, a molecule, and the third one takes the excess energy. And then what is really evaporating? Just the excess, the one which is left with the excess energy, or all three, or what is, how can we view this?
Both of them. So, so if you form a molecule, you get into one of the bound states of this potential well here for a dimer. Mm-hmm. And the energy scale there is so much larger than the energy scales that you otherwise have in your problem, that you have enough kinetic energy that both fragments, usually the molecule as well as a single atom, leave. I guess most of the time it's always a you know, it could be asymmetrically distributed that one of the fragments accidentally has very low kinetic energy, but I think basically that happens. Yeah, I think I mentioned there was one experiment which I just saw recently, but it was a few years ago already at the University of Ulm, where they actually went through some exercise to try to trap the molecules that are produced in this process. But they used a much stronger trap, an ion trap, to trap these molecules. So ion traps, where you have an electric charge that you can actually pull on, of course, are you know, that these are much stronger forces, so you can make a deeper trap. If you just have an optical trap, like in these optical tweezers, you know, you have a Gaussian potential that's fairly shallow and not very deep.
Okay, good, thank you. Looks like there are no more questions, or last chance to raise your hand. If not, then let's thank Joachim, our speaker, very much. Thank you, Joachim.
You're welcome.